Donald E. Knuth presents a simple proof of Tamari's theorem. The set of binary trees with n nodes forms a lattice under a one-way associative law. As a consequence of the associative law, the product of AB times C is equal to the product of A and BC. Any two ways of parenthesizing a formula are equal when variables appear in the same order from left to right. Using the one-way associative law, the product of AB times C can be rewritten as the product of A and BC. This can be construed as a reduction, yielding a right-hand side less than the left-hand side. After presenting a simple encoding of binary trees, Knuth defines an ordering on the encodings. Right rotating a tree increases its encoding with respect to the ordering. The relation and the encodings yield a simple, non-distributive lattice on binary trees.
The title of my talk today is called The Associative Law. I guess you have to come to a computer science lecture in order to hear a lecture about the associative law, because it's so basic in mathematics, everyone stops talking about the associative law in high school in mathematics. In computer science, we're still interested in it. And in fact, it's one of the, I'm going to try to make you all thrilled about the associative law today. Now, in general, when I'm giving these talks, they're based on things that I encounter as I'm preparing for Volume 4 of The Art of Computer Programming. But today is something that really belongs in Volume 1, in a sense that if I had known about the things I'm talking about today when I was in the 60s, when I was writing the first volume, I would certainly have put them in there because that's where we introduced the concept of binary trees. You know, computer scientists, one of the most important data structures that we use all the time is binary trees, and so of course binary trees got right into the first volume of my books, and computer scientists, well, we love binary trees. Let's face it, binary trees are beautiful. They're something that hadn't been studied in great detail in mathematics, but the more we learn about computer applications, the more we're happy we know more facts about binary trees. Now, the facts that I'm going to talk about are some things that are true about binary trees that I didn't know 30 years ago, okay, or I didn't know, in fact, until this summer. I knew that some of these theorems were true, but I was unable to understand the proofs. The main things that I'm going to be talking about today actually were proved by a French mathematician named Tamari in his PhD thesis, and I think it was like 1953. And then he and another French mathematician, Friedman, published in early 60s a simplified proof, but it was still very complicated, and I always thought I would put it on my list of things to understand someday, but it was so long and complicated I never was able to get up the courage to do it. Well, then Tamari and Huang in the early 70s found a simpler proof yet, and so that proof was actually just a few pages long, and if I had known about it, I would have, in fact, read it instead, but I didn't know about that simpler proof until this summer. So then this summer, when I looked at their simpler proof, it occurred to me, oh, but wait, I can make it really simple and nice, and that's when I decided to give this talk. So, but what am I talking about? Well, okay, so first of all, a binary tree, we know, is something which has nodes, and each node has two things coming out of it, or none. So this one has none coming out, and this has two, and we can string these we can string these out in various ways. Now, when I talk about n in this lecture, n is going to be the number of the nodes that have two things coming out. These are the internal nodes of a binary tree. There's also external nodes, and there's always n plus 1 external nodes, and that's where we can hang data. We can also put data in internal nodes, but well, we do everything depending on the application. Now, a lot of algorithms based on binary trees use the idea of a rotation. Let me see. Let me give a more general binary tree here, slightly more general. So let's. Actually, I should let you write one for me so that it's not pre-planned. But let me. But I do have a good one in mind. Well, what the heck? Let's just take a. Let's just draw a few more. Okay, there's a binary tree. How many nodes does it have? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now the idea of a rotation in a binary tree is that we have a substructure that looks like this. There's some tree alpha hanging down here, and some tree beta hanging down there, and some tree gamma down here. These might be complicated, or they might be simple. They might be empty. Alpha, beta, gamma might be empty. Anyway, this, if we convert this into the binary tree that looks like this, with alpha here, beta and gamma here, then we call this a rotation to the right. And then if I move the arrow in the other way, it's a rotation to the left. Okay. Now, this is the simplest thing you can do to a binary tree and get another binary tree with the same number of nodes in it. And it also has a great property that the order of nodes in symmetric order doesn't change. Now, the symmetric order of nodes of a binary tree is when we read them from left to right. You know, this would be 1, 2, 3, 4, 5, 6, 7, 8. The binary. What you do is you first read the things to the left of the root in symmetric order, then you read the root, then you read everything to the right in symmetric order. Or if we projected all of these things down without any lines crossing, it would be the order in which they hit the horizon. And you see that in this tree, if alpha, alpha comes first, then beta, then gamma in the symmetric order, and the same in this on the right. So, in a lot of applications, we'll have the numbers, the data in the tree will be numbers that are in increasing order in symmetric order. So this is a fundamental operation that's often used to balance a tree, to make a tree so that all the leaves are as close to the, that the number of levels is small if we want, or in some cases we like to unbalance a tree and get the number of levels large. Anyway, whatever. Now, we also use binary trees to represent algebraic expressions. And so if I put letters on the bottom here, A, B, C, D, E, F, G, H, I, then this would be an algebraic expression which says we want to multiply B by C, and we want to multiply that by A, and then we want to multiply that thing by DE, and then we want to multiply the whole business times the right subtree, which is FGH times I, right? That's a kind of a mess, but that's another, so this represents an algebraic formula. In that case, if you see what happens to this, what this rotation means, the rotation says that alpha, beta, gamma is being rotated over into alpha, beta, gamma. So this is why I call this talk the associative law. Okay, the associative law is application of changing a formula that has binary operators from this form to this form to mathematicians is the associative law, changing the parentheses. To computer scientists, it means rotating the binary tree. Now, I drew this here as if as if the node on the top where the rotation is taking place is the root of the tree. It doesn't have to be true. You can do a rotation anywhere in the middle of a tree. So I could rotate, for example, well, almost anywhere in the middle of the tree, anywhere that that you have that I have a substructure. I couldn't rotate here because A is not a node. A is just a leaf. But if I wanted to rotate here, for example, then this one would come up, and this would move down. B would so what would happen? A would come up. B, C would attach itself to this guy, and so on. So we would rotate. That would be taking this part of the thing and putting the BC over with the DE, applying the associative law in the middle of the formula. So you don't have to apply the associative law only at the top. Okay, now, interesting thing, though, is when we talk about a one-way associative law. Instead of saying that the associative law is an equality, let's say that instead the arrow, there's a definite thing that this one we might say is unstable and wants to go to this one. Okay. Now this defines not an equality of expressions, but an inequality of expressions. In fact, I'll want to regard this one as larger than this one. We're going to define an ordering on binary trees where this one's going to be a small tree, this is going to be a large tree. And if we ever do a rotation to the right, it's going to make it larger. And then going the other way would make it smaller. So it turns out that we get a nice ordering between binary trees when we consider one-way associative law. This I ran across this first when I was playing with something that got to be called the Knuth-Bendix algorithm, where we're trying to derive consequences of axioms, and the idea is that you want to prove that two things. If you want to decide whether two formulas can be proved equal based on a certain number of axioms, and the Knuth-Bendix algorithm sometimes works, sometimes doesn't. When it does work, it gives you a set of reductions of one-sided transformations that you make, and the idea is that once you got these reductions, you apply the reductions over and over again to both sides of the formula that you wish to prove equal or not. And you keep on doing this, and it turns out that it'll never get into a loop. So each side will reduce to a particular form where no reductions apply anymore. Then the two things are equal if and only if the reduced formula on the left is equal to the reduced formula on the right. So this gives a simple way to test whether it's possible to prove equality of two formulas. Now, if the only axiom that you're given to the Knuth-Bendix system, if the only axiom that you give is the associative law, ABC equals A times quantity BC, then Knuth-Bendix algorithm grinds out one reduction, and this is the reduction it grinds out. And so it says that you can prove that two formulas are equal by the associative law if and only if they reduce to the same thing, which means that if I keep on applying this operation over and over again to some tree, eventually I get to a tree that can't be reduced anymore. And then when you have two trees in that form, then they're equal if and only if one of the things that when I first learned the associative law in high school, it wasn't immediately, I was given that ABC is equal to A times BC, but one of the things I would have to prove is maybe that A times BC quantity times DE, is this equal to, some messy thing, well, let's see, AB times CD times E. And how would you prove that this was equal to this? And you're allowed to use this kind of operation. A, B, and C are variables, not constants. Well, you could fiddle around and get from one to the other, but the easiest way is to keep using one-way reductions instead of going from left to right all the time. Just take this all the way down until finally this becomes A times B times C times DE in a sequence of reductions, and this also becomes A times B times C times D in a sequence of reductions. And so these are equal and these are equal, therefore the original formulas were equal. Well, that's so that's one special case of Knuth-Bendix algorithm. Any of you interested in pursuing what I'm talking about today further, I've got some conjectures that maybe this is going to all generalize to arbitrary axiom systems for which the Knuth-Bendix algorithm works. But let's stick with the simplest case now, this one side of the associative law. Okay, so we got an ordering on binary trees, and we'll say that this tree is bigger than this tree. And whenever I do a rotation, I get an ordering. Now, the theorem that Tamari proved in his PhD thesis in the early 50s was that the partial ordering is actually a lattice. A lattice means that the ordering is kind of nice. You can take greatest lower bounds and least upper bounds in the ordering. This means that if I have two trees, T1 and T2, then I can compute the for example, another tree, T3, that is greater than or equal to T, that's heavier, that's to say larger than or equal to T1 and T2 both, and it's the smallest that's larger than both of them. So anything that's larger than T1 and T2 is also larger than or equal to T3. And conversely, anything larger or equal to T3 is that for T2. It's clear that this relation of greater than on trees is transitive. If I can get from one tree to another by a sequence of rotations, and I can get from that second one to a third one by more rotations, then I can get from the first to the third just by continuing doing the rotation. So the interesting thing was, though, that there is actually a least element that's greater than or equal to 2. And similarly for less than or equal. It forms a lattice and means that I can also take greatest lower bounds. So that there would be some other tree that's less than or equal to both T1 and T2, and it's the largest of all those that are less than or equal. Okay, well now, but the hard thing was proving that. How would you, and not only that, but how would you intuit? How would you understand? Given two trees, what are the trees that are greater than it, are greater than both of them, but as small as possible, being greater than both of them, and how on earth would you compute their least upper bound? In lattice, when we have a lattice operation, we usually call it the meet and the join. This is not the same as a join in database theory, but the meet is going smaller and the join is going larger. And so the meet of two elements of a lattice is written this way and the join is written this way. And well, we'll talk more about lattices in a minute. First, let me show you how we're going to go from binary trees in a natural way to understand what this partial ordering is. So this is the join. And this is the meet, and this is the least. This is the greatest lower bound. This is the least upper bound on two things in a lattice. Okay, let's. Now what I'm going to do is I'm going to encode a binary tree in a very simple way, and it probably was in volume 1. At every node, I'm going to write down the number of nodes in the right subtree. So here, there's 1 here. There's 0 here, 0 here. Here there was 1 node in the right subtree. How many here? 1, 2, 3, 0, 1, 0. Now, the encoding for that tree is we read off these numbers in the symmetric order from left to right. So that would be 1, 0, 1, 0, 3, 1, 0, 0. It should be 8. If there's n nodes, there's going to be n numbers here, and this is so here they are, the right subtree sizes, and this is an encoding anyway, I can take any binary tree and get these numbers. Now suppose that I just had those numbers, but somebody covers up the tree and says, what was that tree? Can I reconstruct it? Okay, well, these are the right subtree sizes of the nodes in increasing order. So how am I going to figure out what's going to happen? Well, for example, this node here has three. It means that there are three other nodes. In fact, the next three have to be its right subtree. So the next three nodes after this one are going to be the subtree numbers. But these, I can draw this arrow here covering three guys to the right, saying that these are going to be in the subtree under this one. Similarly, this one says that it sort of protects that 0 here. This one's going to cover this 0. This one's going to go like that. Now, so I claim that the root of the tree is going to have to be this one, and that these are two subtrees that sort of hang off to the left. In other words, given a sequence of these numbers, we can always convert it into blocks like this, where we draw from every number, we cover that many guys to the right, and these are going to nest. There's never going to be an arrow coming out from under here into another one. You see, I couldn't have a 2 sitting here, because that would mean that somebody would have a subtree of 2 things, but this would all have to be part of the subtree of the 3. Okay, well, now why is it true that this has to be the root of the tree? Well, because if somebody included this as a subtree, it would have to have more than 3 nodes in it, and 3 is the biggest number. So that was too easy. If I started out with a more complicated example, the largest number isn't always the root of the tree, but in this particular case it is. So anyway, that identifies 3 has to be the root of the tree. Then for the right subtree, I have to do a 1, 0, 0. Now, how do I figure out the 1, 0, 0? So that's going to be the subtree that goes over here. And well, 1, 0, 0. Somehow I'm going to have to figure out that 0 is the root of that, and 1 and the other 1, 0 is the left subtree, and so the left subtree will look like that. And similarly, for the 1, 0, 1, 0, we're going to figure out that turns out to be, that the root turns out to be a 1, 0, and that to the left of that is another 1, 0. Did I get it right? Yeah, okay, good. Well, now, how does the theory work? Okay, so anyway, these numbers, it's not really very hard to figure out that you can reconstruct a tree from these numbers, but let's take a look at what the numbers are. So there's a sequence of numbers R1 through R sub n. These are the right subtree counts. And what are the conditions that they satisfy? Well, the first condition they satisfy is that R sub k is less than or equal n minus k. In other words, Rn has to be 0. Rn minus 1 has to be 0 or 1. R1 has to be between 1 and n minus 1, between 0 and n minus 1. Now, well, that's clear because everything in the right subtree, there are n minus k guys to the right, and if Rk represents the number of people in the right subtree, they all lie to the right, then n minus k can only happen if you're using everybody to the right. So this is an obvious condition that has to be true. Now, that's necessary. Another condition is a little trickier, but also true, and that is if Rk is equal to j, that means that we have j guys in the right subtree. That means I was going to draw an arrow past the next j things. Then Rk plus 1 is less than or equal j minus 1, and Rk plus j is less than or equal to 0. And Rk plus 2 is less than or equal j minus 2, and so on. Now, Well, that's what I said after I drew an arrow from this guy to 3 guys to the right. Then the next 3 numbers had to be such that their arrows aren't going to protrude past the arrow that's above them. Another way to say that is the next j numbers, rk plus 1 up to rk plus j. These are the numbers for the right subtree of node k. And so they have to be a proper sequence, as if I put a box around them, these would have to be the R coding of some subtree, and so that would have to satisfy condition 1. And condition 1 would say that the first one is less than j minus 1, the next one is less than j minus 2, and so on, because n is equal to j in that case. So this is just saying, so in other words, condition 1 was obvious. Condition 2 is secondary obvious. That would say that it's a special case. It follows from condition 1 when I look at subtrees. And so you might say, well, then I'm going to have to go to condition 3, which talks about subtrees and keep on going. But it turns out, no, just these 2 conditions are necessary and sufficient. That is, if we have these conditions, then we can always reconstruct the tree. Now you can also put this into another form, another equivalent form. So condition 2 is also the same as saying if 1 less than or equal to I is less than or equal to R sub k, then R sub k plus, right, got to plan ahead here. I forget the if. 1 less than or equal I less than or equal R sub k implies R sub k plus I is less than or equal to R sub k minus I. Isn't that right? Yeah. R sub k minus I. And so I might as well forget this because it works for I equals 0 as well. Okay, so this is the condition that rk plus 1 is less than or equal to rk minus 1, rk plus 2, and so on, going up to that. So here's another way to say this this second condition. But it really means that I just look at the next j numbers, and they have to form an encoding sequence too. So they have to satisfy analogous properties to the whole sequence. Okay, so now if we do that, now I want to say I can, if I have numbers that satisfy this, I can construct a binary tree uniquely that has these as the sizes of the right subtrees. Okay, well, I won't go through a formal proof. It's intuitive, but we get the idea that there is the largest value of k for which the equality, a smallest value of k for which equality holds. It certainly holds true for k equals n. The last guy is always 0. And that there might be earlier ones where r sub k equals n minus k. In that case, I take the very first k, and that's going to be the root of the tree. And so then, so in other words, take k to be minimum, for which k is minimum, for which rk equals n minus k, and then I have rk sitting here, and then I have numbers here, and I want to prove that these 2 guys are going to represent the left subtree and the right subtree of the binary tree. So the numbers on the right are going to satisfy conditions 1 and 2, because condition 2 reduces to condition 1 in the case in that particular case, and condition 2 still holds in the substring if it holds in a string. On the left-hand side, I have to show that R3, for example, is less than or equal. I have to show that condition 1 holds in the left-hand side. So I have to show that R3 is less than or equal to k minus, let's see, I've got k minus 1 guys here. So that would be k minus 1 minus 3. I'd have to show that R3 is less than or equal to I have to show that R1 is less than or equal k minus 2, R2 is less than k minus 3, R3 is less than k minus 4, and so on up to Rk minus 1 is 0. Now, how would I show that R3 is less than or equal k minus 1 minus 3? Well, if not, because R, well, let's see. Okay, so R3 plus k minus 3. If not, if R3 were, if not, then it would be then it would be k minus 3 or more. So then I could talk about R of 3 plus k minus 3, and I could call J, this would be I. So then k minus 3 is less than or equal to R3, and then so I apply I k minus 3. This is R3, and so then it would say that R sub k minus 3. R sub 3 plus k minus 3 is less than or equal to R3 minus I. But that's less than or equal to n minus 3 minus k minus 3. So let me see, what am I doing here? Well, this is equal n minus k, but this is rk. Yeah, rk is this, and this is n. Okay, so this is n minus. This is equal to n minus k. This is equal to rk again, by my assumption. So equality has to hold everywhere, and this would imply in particular that R3 was equal to n minus 3. But I assumed that k was the minimum. Okay, long proof, but that proves that this works. So if you have conditions 1 and 2, you can always construct a tree from them. And the tree, that was the only tree that does it too. It's easy to see that that's unique. Okay, now let's look at what a rotation does. What does a rotation do in this encoding scheme? So suppose I have a rotation, and I got R things here, which means that that gamma has R guys in it. R nodes are in gamma. And suppose I have Q here. So there were Q internal nodes in beta. And now I rotate that, and I get another tree with alpha here and beta gamma here. Now, inside alpha and beta, nothing is happening to the sizes of their right subtrees. If this is in the middle of some bigger tree, nothing is happening to the size of anybody else's right subtrees either. But what's happening now? The size of this subtree. How many nodes are there? Well, there's Q here, R there, one more there. So that's Q plus R plus 1. And this is still R. It's still gamma. So what's happened in a rotation is that exactly one of the subtree counts has gone up. And it went up from Q to Q plus R plus 1, which is definitely bigger. Okay? So certainly, if I have some row represents some tree, and then I rotate, this goes to let's say row goes to row prime, then this is true. Then it's true that row is less than or equal to row prime component-wise. Let me use this less than or equal on a row here is going to stand for a sequence of numbers, like 1, 0, 1, 0, 3, 101. And I do a rotation, any rotation whatsoever in that tree. Whatever I get I'm going to get something that component-wise, the first component is less of rho is less than the first component of rho prime, second component less than or equal, and so on. In fact, it's going to be equal everywhere except in one place. But so it's quite clear then if I do a sequence of rotations, then it stays component-wise larger. Okay. Now the beautiful thing, and otherwise I wouldn't have given this talk, is that it also is true the other way. In other words, rho is less than or equal to rho prime, or let's say rho rotates with a star in here that says a star means that I apply a rotation 0 times, 1 time, 2 times, any number of times. If and only if it is component-wise less than in its when I read the numbers. So if I look at the encoding of any two binary trees and I compare them, I compare R1 to R1 prime, R2 to R2 prime, and so on. If I always get less than or equal, then I could get the second tree from the first by doing rotations only to the right. But if any one of them is less, I obviously couldn't. Now one way is obvious. It's this way. It's saying a rotation always increases. But now we have to show the other way, that if I take any two binary trees and one is bigger than the other, then there is a way to actually rotate the guy into the other one. I'll prove that in a minute. We'll first derive some consequences of it and see why that's interesting. But that is a fact, and we'll soon see why it's true. And so this is a very nice characterization. You just look at these right subtree numbers, and then as we first saw, knowing the right subtree numbers is enough to know the tree. And secondly, if you know the right subtree numbers of two trees, you can tell whether one is less than or equal to the other. One is obtainable from the other by rotations or not. It's just look at them component-wise, and each component has to be greater than or equal. Okay, but now we can also get a corollary, and that is the join, or the meet, I'm sorry, of two trees is equal to the minimum of the two component-wise. If I take the encoding of two different binary trees, and if I take the minimum component by component, independent of anything else, I claim I get the encoding of a binary tree, and then therefore it would have to be be the greatest lower bound. Okay, let's see why that is. First of all, suppose I have sequenced then R1, R2, Rn, and another one, R2 prime. So these are two encodings of binary trees. So it's equivalent to saying a binary tree is given by a sequence of numbers. This is rho prime. And so this satisfies conditions 1 and 2. R prime satisfies conditions 1 and 2. Now I just want to show that the minimum of the two, minimum of R1 prime up to minimum of Rn prime, that this sequence also satisfies conditions 1 and 2. If I can show that it satisfies conditions 1 and 2, then it represents a binary tree. Okay? So, well, that's obvious. I mean, take condition 1. Rk is less than or equal this. Rk prime is less than or equal this, so the minimum is certainly less than. On the other hand, here, let's suppose that Rk is well, I can do it in this form. So suppose I is less than or equal to the minimum of Rk and Rk prime. Then I have to show that the minimum of this is less than or equal to the minimum on the right-hand side. But well, it's obvious. I mean, the minimum of Rk plus I and Rk plus I prime is less than or equal to the minimum of RK minus I, and RK prime minus I, because if you take the minimum of two things, so this one is less than or equal to this one is less than or equal to this, and this is just the minimum of RK prime minus I. So condition 2 holds as well. So in other words, if these two conditions hold, then so does it also holds for the minimum. It doesn't hold for the maximum. We'll talk about the maximum in a minute, but it certainly holds for the minimum. Okay, so in other words, this is a simple operation now to do component-wise on any two encodings, and it gives us another tree. So that's a binary tree. The significance of that binary tree is it is less than or equal to this one, and it's less than or equal to this one. Therefore, this binary tree will rotate into this one and this one. It's a common less than or equal to both of them. And it's the largest such, because if anybody is less than both of them, it has to be less than or equal this one. This is the biggest we could possibly get. And anything else less than both of them would have to be less than or equal to the minimum of the two guys. So that's the proof that there is a greatest lower bound. I haven't proved this, I haven't proved the other side of this law, but as soon as I prove that, then I've got a greatest lower bound. To get a least upper bound, we do the same thing, but we use left subtree encoding instead of right subtree encoding, and then we take the minimum of those. And if you take so there's a duality between left and right. If you switch left and right, then less than goes to greater than. Left rotation goes to right rotation. So it's flip left and right. You get an equivalent theorem, and you're taking the minimum of those encodings will give you a left subtree encoding for a tree, and that will be less than or equal to in the dual version, so it's greater than or equal in the other one. So we can compute the least upper bound in a similar way, but using left subtree sizes instead of right subtree sizes. Now, I still have to prove this this fact here, and it's not hard. Now I'm going to work on another problem. So I'm going to erase this. I'm going to say, suppose this is less than or equal to this, but not equal. And so now I'm going to try to prove this direction. I'm going to try to prove if I have two sequences, this one less than or equal to this one, then I'm going to prove that I can rotate this tree into this tree, that there is a rotation. So let's suppose that R1 equals R1 prime until we get RK minus 1 equals RK minus 1 prime. But then we have a definite less than situation. And then after that, RK plus 1 is less than or equal RK plus 1 prime, and so on up until RK all the way up to R sub n is less than or equal R sub n prime. So I have a less than or equal situation on the right, equals to the left, and definitely less than right here. And now I want to show that I can do the rotation. So the idea will be simply to say that there's a rotation that will increase RK and keep it less than or equal RK prime. So if I can find some tree, if I can do a rotation here, that'll increase RK, but it won't change any of the other. Remember, a rotation only changes one of the R's at a time. So if I find a rotation, so I'll do a rotation at this node, wherever it is. I'll want to prove that it has that its parent is a right parent. That K, node K, has to be a left child of its parent, and that if I do a rotation at K, bring it up, then the new value that it has will be less than or equal to RK prime. And if I can do that, well, then I've gotten closer. I've rotated this one. I've gotten closer to this one because something increased, and so I can keep on repeating this over and over again. Eventually, I get there. Okay. So this is the crucial step is saying that if I get a rotation, then I made progress, and this progress, you know, I can't, this can't go on forever because these are finite numbers, so okay, so that's the way it works. Now, if we look at the right encoding, it turns out that well, I have to show that, as I said, that K, node K, that I could do a rotation there. I mean, I have this node, the kth node in symmetric order, and it looks like this. And then it's got, I want to show that it has a parent up here, so that I can do a rotation, and then there will be a certain number of nodes here. This will be R well, let's call it L. L is equal to, you see, what node is this? What is the Lth node? This is node, the kth node. The right subtree here is has RK nodes in it, so L is equal to K plus R sub K plus 1. Or is it? If RK is 0, that means there's nobody here. Then L, yeah, that's, yeah. So L is K plus RK plus 1. It's the, and so if we look at it in the sequence form, RK is sitting here, and we draw an arrow over the next R sub K nodes, and then R sub L is the node that follows after it in the sequence. I think this geometric picture is the easier way to look at it. So I've got so I've got this kind of a picture. Well, now if I do a rotation, then at K, I'm not going to write out the proof, but it's easy for you to find by yourself if you do it. But it follows from conditions 1 and 2. Remember, condition 2 said that as I draw this arrow in here, everybody inside the box is another sequence that satisfies conditions 1 and 2, but with the size of the subtree. This sequence here represents some subtree. So now, okay, the fact that I never used this. I never used the fact that RK prime is a larger value here. In other words, that RK prime is another tree that actually works, and it's bigger. RK prime is bigger than RK. So the arrow coming out of the second one shoots out to the right. So that means there's an enclosing box out here that is there's a constraint on how big R sub K can get, and that constraint is not tight when I draw this arrow, because RK prime also meets the constraint. RK prime satisfies this condition too. So RK prime can't be, RK can't be too large, and therefore RL, which sits inside this box, is also under this same constraint. That's going to be the key that proves that there is a node above it. The only nodes that don't have a right whose parent is not to the right are the ones for which, when you draw the arrow went as far as it could go. So if there's another arrow above it, the arrow goes all the way to the right. If the arrow comes down like this, then then this guy's going to be a parent of this subtree. But if it comes all the way to the right, then it doesn't have a parent to the subtree. So that's the idea, that this value here, R sub L, is known to be not too large. It's because RK prime puts a bound on this. This guy can be at most RK prime minus 1, RK prime minus 2. This can be at most RK prime minus RK plus 1. And so when you put the whole thing together, you do get, in fact, exactly the inequality that you need. Okay. That proves the theorem, but now let's try to intuit it and figure out what it means. So, for example, I've drawn all the, here I've got a picture that shows you all the trees when n equals 4. N equals 4, so I have 3, 2, 1, 0 is the largest tree that you can get, that's 3, 2, 1, 0. That's a tree that's you can't rotate anymore. This is the only one that you can't rotate from. And at the bottom here, 0, 0, 0, 0. This is the extreme 0, 0, 0, 0. That you can, the only thing you can do is rotate. So this is the bottom element, the very smallest. This is the largest. This is the top element. And then, since I have 4 numbers, but the last number is always 0, I can draw them in 3 dimensions. The other 3. So you can imagine that this is a 3-dimensional picture here. And so I gave the x and y and z coordinates. And going up is a rotation. Or going up in any either x, y, or z direction is a rotation. So we can go from this tree to either the 1, 0, 0, 0, the 0, 0, 1, 0, 0, 1, 0, 0. Okay? So the 14 trees are now encoded by strings by their right subtrees here. Let's think of an analogy. Imagine another lattice. It's easier to think of. Consider all the divisors of 360. So 360, if I've done this right, is 2 cubed times 3 squared times 5. 8 times 5 is 40 times 9. Yeah, and so now the 5 to the first power. So all the divisors of 360, we can encode them by how many 2's are in them, 3's are in them, and 5's are in them. So the divisors of 360 can be represented as a sequence R1, R2, R3, or R2, well, anyway, 3 numbers, where the first one is 0, 1, 2, or 3, the next one is 0, 1, or 2 for how many 3's there are, and how many 5's are 0 or 1. So we would get a picture something like that, but it would be a complete brick. Then I draw up here the corresponding thing for when you have a multiple of 5. So it gives you, so I get something like this. Did I do it? Did I blow it? It's not too bad. This is going to be the top of the brick. And then we got vertical lines going down. So there's a grid here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be 0, 0, 0, 0 again. 0, 1, 0, 0. This would be 1, 0, 0, 0. And then up here is 0, 0, 1. Forget the last component, excuse me. And at the very top is 3, 2, 1. Okay, it's a similar thing, but we have all possible coordinates here. Here it's a sparse thing. We have to leave out the coordinates that don't satisfy conditions 1 and 2. All right. So this is a lattice. In fact, that might be why they started calling them lattices in the first place, because this is like looks like this is all the lattice points in a solid. And when we talk about 2 numbers that are divisors of 360, we talk about their greatest common divisor, their least common multiple. The greatest common divisor we obtain by taking minimum component-wise. How many powers of 2 divide the thing, how many powers of 3, and so on. Least common multiple, we take max component-wise. Now, in this case, if we take, but what does it mean when you, in this case, we got only a part of that brick. So in this lattice, what happens when we want to take the join of 2 trees, the corresponding thing to least common multiple or the least upper bound? And the answer is, well, you take the max component-wise, but then you have to go up, but that doesn't necessarily satisfy conditions 1 and 2. So then you have to find but you look at all the things that do satisfy conditions 1 and 2, and you find the smallest of those. You take the minimum of all of them component-wise. So you take the set of all of the guys who are greater than or equal to the max component-wise, and take the intersection of all those, and the minimum of all those, and that gives you the value. I told you another way to get it by left subtrees, which which is faster, but this is another way to do it. So if you have two trees and you want to take their least, you want to get their least upper bound, well, you can look at the max component-wise and see if it appears here. If it doesn't appear here, well, you've got to go up to something that does. But the least one that does will be unique. There won't be two that are there. Okay, so that's because it's a lattice. And the proof is by using the other calculation by means of left subtrees. Now, in some ways, this is, okay, now this analogy might give you the wrong idea about trees because the lattice of divisors is a distributive lattice. It satisfies the distributive law between lobes and globes. But this is not a distributive lattice. This lattice does not satisfy the distributive law between least upper bound and greatest lower bound. In fact, I think that the lattices you get from binary trees are probably the most interesting lattices that are not distributive. And you know, for textbook examples, this would be I think the best of all the lattices that are not distributive. This one will be the one that has the most neat property. Now, other things to observe here is that if you add the numbers here, the sum of all the r's, in a distributive lattice, the sum of all the components it turns out to be the distance to 0, 0, 0. That every time you take a step, you increase by 1 the sum of the components. So this 3, 2, 1 here is 6 steps away from 0, 0, 0. And by all paths, whatever path you take, you always go down by exactly 1. But in a non-distributive lattice, that doesn't happen. But the sum of these numbers does have an interpretation. It's the length of the longest path to 0, 0, 0. Because you can see that if you pick off the numbers from the right to the left, so 3, 2, 1 will go to 3, 2, 0, 0. It's got to sit here. Here it is. And then 3, 2, 0, 0 to 3, 1, 0, then into here, and then down here. There's always and this is true for any tree. If I do the rotations in a dumb way, I can rotate it so that exactly one of the r's goes down by 1. The rightmost r that's non-zero goes down by 1 each time. Okay, so that's an interpretation of the sum of them. But now the distance to 0, 0, 0 is another thing that's easy to characterize, and you can do this in terms of the number of blocks of top-level blocks here. Now, when I say a top-level block, I mean when I draw an arrow, I group these two together, and so there are 3 top-level blocks here. If I had 0, 0, 0, that would be 0 by itself is a block, but then if I have 1, 0, this would combine it and so on. This has 4 blocks. If there are k blocks, the distance to 0 is n minus k. And it's obvious because every rotation, if we look at rotations in terms of blocks, it's easy to interpret it. Namely, I had a rotation which had the value q was sitting here, and then that was drawn over a block. And then I had an r here, and that was drawn over another block. That was before the rotation, and then this sits inside some larger encoding. This was before the rotation. After the rotation, what happened? I got q plus r plus 1, and so everything else stayed the same inside, but the number of blocks decreased by 1. And so every time you do a rotation, you decrease the number of blocks by 1, unless this is already living inside of some other block, in which case the total number of blocks stays the same. So if you've got 3 blocks, you start out with n blocks, and if you end up with 3 blocks, you could do it in n minus 3 steps, because each time you lose 1 block. So it's easy to see the distance to 0 is the number of blocks in this, which is also the path along the subtree. So the shortest distance from any place to 0 is at most n minus 1. Another thing you can notice in this picture is that every vertex has degree n. There's always n things there's the up degree and the down degree. But the sum of the up degree is, increasing x, y, or z, and the down degree is the other way. But the sum is always 3, and that's true in general. The sum is always n. If I would look at this construction, and that's because I'm sorry, n minus 1, and that's because there are n minus 1 nodes that aren't the root. And so you can do a rotation at any of those. It'll either be a left rotation or a right rotation. Now, when you talk about lattices, it gives you extra intuitions and things that you can do about trees that otherwise you couldn't do. I mean, you might say, what's the good of all this? And people talk, for example, we have prime numbers in, and for the divisors, we can they talk about the join irreducibles and the meet irreducibles, which correspond to powers of primes in the case of divisor lattice. So the same. So these are the nodes that I've checked here. This would correspond to 2, 4, 8. This would be 3, 9. This would be 5. Those are divisors. If I know how many times these divisors divide a number, then I can figure out, for two numbers, then I can figure out their GCD. The same thing holds in a lattice. That is, there's a kind of a factorization theorem in a lattice that says that any, in the case of trees, this would say that any tree can be written as the join of join irreducible trees. And any tree can be written as the meet of meet irreducible trees. So what are the join irreducible trees? The join irreducible trees are the ones that have non-zero in exactly one component, exactly as there. So here's a join irreducible tree. These are the join irreducible trees. Now the meet irreducible trees are, there's also 6 meet irreducible trees, and what you do is you start out with, this is too small an example to illustrate it, so let's take a larger, suppose I have 7 nodes. And I start out with 6, 5, then n minus 1 all the way down. This would be the top element of the lattice. And then I take some subinterval and I zap it, which means I decrease it down as small as I can. I decrease it so that it ends with 0. And all the things that you get by zapping, those are the meet irreducibles. And so I can represent an arbitrary tree like this one as the meet of meet irreducible. So the prime factors of this tree, in a sense, are the things I would get by zapping. I could take this is 8, 7, 6, 5, 4, 3, 2, 1, 0, and then here I zap. I zap here, so this gives me a 1, 0, 7, 6, 5, 4, 3, 2, 1, 0. And then here I'm going to get 7, 6, 5, 4, I think 3, 1, 0, 0. I just have to zap there, here, and here. And now I take the minimum of these component-wise. I get my 1, 0, 1, 0, 3, 2. So the meet of these 3 trees is this one. And so in some sense, this is a prime factorization of the trees. So it gives us another way to look at trees, and we can think about operations about binary trees in a way that would have not been clear before. One last thing I want to mention is that it's been is that a lot of people want is the interpretation in terms of triangulations of polygons. So the number of binary trees is Catalan number. There are 14 here, for example, and with 3 nodes there are 5. With 2 nodes there are 2, so it goes 1, 2, 5, 14, 42. Very famous sequence. And the reason it's famous is that there are some 80 different combinatorial problems known that all have Catalan numbers as the solution as to how many ways there are to do it. And so for every one of these interpretations, there's a corresponding notation thing corresponding to the associative law, corresponding to the idea of a rotation when you put it in that interpretation, in that combinatorial interpretation. And one of the nicest combinatorial interpretations is in terms of polygons, where we talk about triangulation of a polygon. This is one triangulation of a polygon. If the vertices of the polygon are A, B, C, if we call the sides and give them letters, and then we have the base and we leave it off, then we can get a binary tree in the following way. We multiply B by C, and so that's BC here. Then we take that and we multiply by A. That gives us this line. So each diagonal line corresponds to a node in the tree. Then here's a product of D times E. And then if we multiply that by F, we get this one. And then finally, this is the connection. So there's a correspondence between putting the diagonals in a polygon till you have triangles left and a binary tree. If you say, well, what's a rotation in this case? Well, it just turns out to erasing one of the diagonals and putting in the other one. And that's called a flip operation. And people who do computational geometry, triangulations are very important in numerical analysis. But a lot of operations are based on this flip operation inside of things. And there's a right flip and a left flip, depending on whether the node that you're flipping is, or the diagonal is sort of cutting from left to right or right to left. So you get a lattice of polygon triangulations. And if we now ignore the difference between left and right, and just look at this as a graph, undirected graph, this is a graph where every vertex has degree n minus 1. And one of the important questions that have been studied, like, for example, in connection with something called splay trees, is the minimum number of rotations to get from one tree to another. That's the distance in this graph. The distance, since we know we can get from anything to 0 and back again by in n minus 1 steps, so 2n minus 2 is a bound. But there's a paper that I just started reading a couple hours ago by Slater, Tarjan, and Thurston, where they proved first by a very nice simple argument that 2n minus 6 is always an upper bound, as long as n is greater than 10. So if you have n is 11 or more, you can always get from any tree to any other in 2n minus 6 rotations at most. And then they prove, by an incredibly complicated argument, that for infinitely many cases, this bound is tight. That for infinitely many values of n, there are trees with n nodes that are exactly 2n minus 6 apart in this graph. And they prove it for all n of the form 10 times the perfect square, provided that this number is greater than 2 to the 60th or something like that. So it's been proved that there are infinitely many cases, but they conjecture that it's true for all n greater than 10, and it's known up to n equals 20 by calculation that the diameter of this graph is 2n minus 6 in all those cases. So there's got to be a combinatorial proof of this, and they use hyperbolic geometry. If anybody knows Thurston, you're not surprised that that's the way he would do it. And what I suspect might be nodes that are maximally far apart are like this. If you do a triangulation like this in one polygon, and then you do a corresponding one like this, cutting across it in the other, then it seems to me that that's going to take a lot of flips to get from one to the other. But proving it might be difficult. Yeah. To summarize, anyway, having this lattice theory knowledge is going to, I think, give us add yet more to our intuition about binary trees, and it's one of these nice facts to know that that the set of all binary trees actually has an algebraic lattice structure, and that by looking further at this and thinking about prime factorizations and other things, we can see new things about trees that we didn't see before, and this might be just the thing we need to solve the next problem we need to solve with respect to binary trees. Who knows? Okay, that's it.